everybody, let's continue Unit 3 and let's move on to Lesson 2, which starts on page 13 in your book. Okay, page 13. So today we're going to be talking about the scaling principle. All right, this is using dilations. Okay, so this is the fourth of the transformations. Remember we talked about translation, rotation, and reflection were just ways of moving a figure to like a new location without changing the size. And the fourth type of transformation, dilation, does change the size. It either makes it bigger, which is called an enlargement, or it makes it squish smaller, which is called a reduction. And we use scale factors to make sure that we enlarge it or reduce it by exactly the same amount in all directions, okay? So here we have two parallelograms. This first parallelogram has a base that's 4 units long. This side would also be 4 units long. And the height, which goes up at a right angle from the base to the other side, is 2 units long, okay? So this is our original figure, and we're moving to that figure. And you can see that it got bigger. It's definitely an enlargement, got larger. And we can see how much it got larger because the height was 2 units. Now the height is 6 units, okay? So it went from 2 units to 6 units, and the length went from 4 units to 12 units. So can you see what we're multiplying it by? The scale factor would be 6 divided by 2 or 12 divided by 4, which is a factor of 3. We're multiplying times 3. Okay, you multiply by a scale factor. Okay, so 2 times 3 is 6, 4 times 3 is 12. Look what happens to the area though. So remember, the area of a parallelogram is just the same as it is for a rectangle. It's the base times the height. So the base is 4, the height is 2. So if this is parallelogram 1 and this is parallelogram 2, the area of parallelogram 1, base times height, is 4 times 2, which is 8. But look at the area of parallelogram 2. The base is 12, and the height is 6, and that's 72, 6 times 12. So this did not go up times 3. 8 times 3 is only 24. This actually, to go from 8 to 72, is a factor of 9. Okay, so the area of the small parallelogram times 9 to get to the large parallelogram. Okay, so the scale factor affects one of the dimensions, the length or the width. It does not affect the area. Okay, the scale factor is for each dimension. Okay, so the factor for the area is not the same as the scale factor. All right, so let's do a little experiment here. Let's explore this. If we have a triangle here, the original triangle, remember the area of a triangle is 1/2 base times height. So it's 1/2 times the base of 8 times the height of 3. 1/2 of 8 times 3 is 12. Okay, so we're going to write that at the beginning of our table here. So we know that this is 8 times 3 over 2. Whoops, over 2. Sorry, I can't write here. 8 times 3 over 2, which is 12. Now, what if we had a scale factor of 3? That means that instead of 8, it's going to be 8 times 3. And instead of a height of 3, it's going to be 3 times 3, or 9. Okay. Then what happens is the area of that larger figure is going to be 1/2 of base 24 times height of 9, which is going to be 108, all right? So the ratio, if we compare this new one to the original one, is 108 compared to 12. Well, 108 divided by 12 is 9. All right, it's the same as what we did on the original one. Remember, we scaled everything times 3 and the area went up times 9? What if we had scaled it times 2? We would still have the same 8 times 3 divided by 2 for 12 of the original, but now the new one, we're factoring everything times 2. So the base, 8 times 2, which is 16, and the height, 3 times 2, which is 6. So the new area is going to be 1/2 of 16 times 6, which is 48. Right? So let's compare 48 compared to 12. The factor would be 48 divided by 12, or 4. Okay, do you guys notice a pattern here? When the scale factor is 3, the area factor is 9. When the scale factor is 2, the area factor is 4. 9 is 3 times 3, 3 squared. 4 is 2 times 2, or 2 squared. What if we scaled them down? What if we made it smaller? Okay, so instead of having a base length of 8, which is what we're starting with, what if we cut them all in half? So now the base is only going to be 4. It's going to be half of 8. And the height, instead of being 3, it's going to be half of 3, which is 1.5, 1.5. Then the area of our new smaller triangle would be 1/2 times 4 times 1.5, and that is 3. Okay? So our new area is 3 compared to the original one, which is 12. Well, 3 divided by 12 is 1/4. 1/4, you guys, is 1/2 times 1/2, or 1/2 squared. Okay? And the same thing happens with 3/2. We start with 12. The base becomes 12, which is 3/2 times 8, and the height becomes 4.5, which is 3/2 times 3. The new area is 27. Okay, and if you compare 27 to 12, 27 divided by 12 is 9/4, which is 3/2 times 3/2, or 3/2 squared. So see what's happening? When we have a scale factor, it affects the length, or the base. It affects the height. So we have a scale factor this way and a scale factor this way. So we need to use the scale factor twice on the area, right? All right. So here, in fact, is the rule for the scale factor. Okay, the scaling principle for triangles is if similar triangles are related by a scale factor of, let's call it A, then their areas are related by a factor of A squared. Okay, so if the scale factor is a. The areas have a factor of a squared, okay? And in fact, it's not just for triangles, it's for any polygon. So the exact same rule, if similar polygons, that means they're a dilation. If similar polygons are related by a scale factor, we'll call it A, related by a scale factor of A, then their areas are related by a factor of A squared, okay? If the scale factor is A, the areas are A squared. So look at what that means in this first problem. We don't know what the dimensions are, but we know that we do know what the dimensions are. We know that this is 16. We don't know how wide it is. B, we know this is 30. We don't know how wide it is, but it's a scale factor. Okay? We know it's a scale factor. And they're saying the area of this one, of the little one, is 88 millimeters squared. We don't know what the area of the big one is. Well, we can figure out the scale factor. So the scale factor is, what are you multiplying 16 times to get 30? And you calculate that by doing 30 divided by 16. And 30 divided by 16, it's not a very pretty number. It's 1.875. Okay, so that's the scale factor. That's like our A. Okay. So we're multiplying the base times that factor, and we're multiplying the height times that factor, which means we're multiplying the area times that factor squared. That's like our A, okay? So then the area of B is going to be the area of A times 1.875 squared. We have to multiply times 1.875 times another 1.875, okay? In other words, the area is 88 times 1.875 squared. Again, grab a calculator, and the answer is 309.375. And we were using units of millimeters, and its area, so it's square units, all right? Okay, so I wanted to show you one more thing, you guys, because so far we've been talking about scale factors where both the base and the height, or the length and the width, are multiplied by the same number. And if you are doing a dilation, you have to use the same scale factor for both measurements, right? Everything has to grow by exactly the same factor. But you might have a problem where, and I'm just going to draw this freehand, okay? What if we have a rectangle, and let's say it's 4 by 2 feet. So the area is 4 times 2, or 8 feet squared, okay? But what if we have different scale factors for base and height? Okay, what if it's not the same? It's not a dilation. It's going to change the shape, okay? Because what if our new rectangle, what if the length was 12 feet, and what if the height was 4 feet? Okay, so what's happening, you guys? Look at this. How is this changing? So the scale factor for the base went from a 4 to a 12, which means it was times 3. But look at what happened to the height. It only went from a 2 to a 4, right? It only doubled. okay? So the length tripled times 3, the height only doubled times 2. It's not the same factor, okay? Not the same scale factor. So look what happens to the areas. Just real quick, I want to show you. The area for the first rectangle was 8, right? What's the area for the second one? The area for the second one is 12 times 4. 48. So how did the area change? The area went from 8 to 48, right? The new one is 48. The original one is 8. Well, you guys, 48 divided by 8, it went up times 6. 3 times 2. It went up by a factor of 6, okay? Because the factors were not the same, so you're not squaring them. It's two different factors, so you multiply them. Okay? You'll see more about that later on, but that's enough for today. Bye, guys.